Okay, so we've covered some introductory concepts, and we've touched a little bit on, we're talking about light, we're talking about radiation, we're talking about, how do we actually do astronomy? How do we actually learn astronomy? So what we want to talk to you about now is telescopes, and this is how we do astronomy.
Yeah, modern astronomy really began in some sense in 1610 when Galileo built a telescope and pointed it at Jupiter and the Sun and Saturn. And so much of what we know is based on looking at things through telescopes and trying to understand it. That's a very broad saying because we have very different kinds of telescopes. We use them in different ways. And there's really, it's almost incorrect to say we use a telescope to understand astronomy because that term is so broad. So when you think about telescopes, you probably think about the thing behind Kate's right shoulder here. This is probably, 10 to 14 inch telescope. You might have something like this that you've looked at in your backyard before. It's what a lot of telescopes do look like.
And these even vary so much. You get telescopes like this that are, primarily mirrors, and you get telescopes, that are your typical refractor telescopes that are full of lenses. So I guess one of the main benefits of, moving from the human eye to telescopes is the light collecting area, and actually being able to collect photons from objects and focus it and create an image that we can actually see with our eye, which is what you're doing when you look through these telescopes.
Right. And you might have done this yourself before. If you've looked at the night sky with your eye, you've seen what stars you can see, and then you look with a set of really good field binoculars at a galaxy, you can see it better, and then you look with a telescope, you can see this galaxy even more beautifully. A lot of what you gain is just having more photons that are being combined through lenses and mirrors into a small space for your eye to see. And so a lot of the benefits between the first Galilean telescope and roughly 1900 was just bigger and bigger telescopes to collect light for a person to look at through an eyepiece and see things that they couldn't see with their own eye.
I would encourage you to do some research on this because as Ben said, this whole, history of telescopes got ridiculous. The types of telescopes that people were making to try and optimize the focus and the light collecting area, it just got to a point where, do some research on it. People are, these massive, long telescopes that are, supported on struts and everything. I mean, it just got... Of course, the focusing was just absolutely impossible in something like that. But this is what people were trying to do. People started to understand how to get better viewing. And so they would, keep modifying these telescopes to something that became, it started, outdoing the technology at the time.
Yeah, there's been really, really interesting engineering problems that have come up and then been solved as you move to building larger and larger and larger telescopes. So these days, a lot of the ones that are used in modern research are measured in meters. The largest telescope in Australia that's used, the largest optical telescope in Australia that's actively used for research is the AAT, the Anglo-Australian Telescope, which is near Coonabarabran. It's about 4 meters in size. I'm a little under 2 meters. It's stacked both of us together on top of each other. It's still bigger than us. We'd be kind of uncomfortable.
Yes. Yeah. But there are also obviously lots of engineering problems with this too, because as you start building mirrors that are larger and larger, then you start running into, practical engineering problems around that.
Yeah, it really gets difficult above about 8 meters, which are some of the biggest telescopes we have are 8 meters in size. There's the engineering problem of as you tilt it to look at something, you need to make sure it stays steady so that the lens, the shape of it can reflect light into a single eyepiece detector, whatever you're looking with. There's also the issue of if you build an 8-meter thing, you have to move an 8-meter thing. We often put telescopes in very remote places that don't have the engineering capabilities to build a 10-meter class telescope right there, so it's built somewhere else and shipped to a location. That gets challenging.
Yeah, and it's worth pointing out here that obviously, you know, when you have a telescope like this, you're actually collecting the photons in your eye. But when we start doing things like these massive telescopes that Ben's talking about, typically people are not looking down an eyepiece for these things. We start having detectors that are actually measuring the photons for you.
Yes, makes our lives a little easier. And so a solution around that is building what are called segmented mirror telescopes, where you have a bunch of little segments that are, you know, a meter or a couple meters in size that all work together to build one image. For example, the Keck telescope in Hawaii has 36 hexagonal mirrors that together build a 10-meter aperture, but each individual one a person can carry and move around. And so it's you know, easier to build, easier to maintain. And the James Webb telescope that was just recently launched and is now active out in space is built on the same principles.
And it's worth noting too that these, this sort of, I guess, scientific and engineering feat of, you know, segmented mirrors and stuff, this is not a new concept. I mean, people, I believe it's in the University of Bologna. They have a telescope that was built into the building, and it had a bunch of segmented mirrors down the bottom. However, the thing that they had to do to, you know, now we have computers that actually can move the mirrors for us, whereas they used to have someone that was down in the bottom room turning screws while there was someone at the top telling them when they were in focus. So that is just... this is what I mean when I was saying sort of like, you know, they were going further than what engineering could actually do at the time.
Yes, yeah. A lot of it got much easier in the 1980s once computers could help us.
Yes,
yeah.
And actually this is a really good point to move on to, because you just mentioned James Webb. And, you know, maybe you've thought about this, maybe you already know the answer, but, you know, we have telescopes on the ground, but then we also send telescopes into space.
We do, absolutely.
Yeah.
And there's lots of reasons to want to put a telescope in space.
Or on a really high mountain, but space is even better.
Yeah, space is even better. The first problem with the Earth, you might not think that's a problem, but I do, is that it has an atmosphere. And so that gets in the way of a lot of your observations. We see stars twinkling at night because the atmosphere is time varying. There's wind and turbulent processes in the upper atmosphere that cause everything to move around. And so your light gets scattered from being one single point from the star to something that spans a couple arc seconds on your sky. And so we can do some novel tricks to try to correct for that using lasers. It's called adaptive optics. But in space, you don't have to worry about that at all. Other problem with the Earth is that there are some wavelengths where just our atmosphere is completely opaque. If you are trying to look in the near infrared, for example, light doesn't transmit. This is kind of the underlying physics of the greenhouse effect, that, you know, light comes in from the sun and then gets emitted at infrared wavelengths but can't escape, and so it keeps the Earth warm.
Which is great for humans, but not great for astronomers.
Great for humans that aren't astronomers. Good for humans that are astronomers, but bad for astronomy.
Yes.
And so if we want to observe at those wavelengths, there's many in the ultraviolet and in the near infrared that are especially bad from Earth. You need to be above the Earth's atmosphere. And then also there are some science goals that, you know, if one of the main efforts of exoplanet research is to try to find planets with biosignatures, you know, things where you have signatures of, you know, an atmosphere that looks like the Earth, has things that are signs of life. It's much harder to measure those if you're looking through the Earth's atmosphere, because those are all going to be in your data anyway, because you'll have the Earth's atmosphere. And so for some science cases, you just, you know, want to be looking from space. Also, when you're in space, you don't have to worry about the Earth getting in the way. We can only observe at night. If you want to observe continuously for a year, if you're trying to, you know, find planets or look at something that varies in brightness over weeks or months, you can't do that from the ground because you only get, you know, at best 12 hours a night. But from space, you can just observe continuously.
Which reminds me, actually, we're going to talk more about observing seasons later on this week. So Ben will touch more on that. But yeah, is there anything else that we want to say about telescopes?
I think we've covered the big things. You'll explore telescopes and data from telescopes more over the term. What's your favorite telescope?
Oh, good question. What's your favorite?
I just kind of like them all.
I like them all too.
Yeah. No, my favorite is the Kepler telescope.
Why?
It's the first telescope I really did astronomy with, and it's taught us so much about stars and star spots and planetary systems, and it really changed the way we can observe the universe, the way we understand the universe, and it's really, really fun to work with.
We will put an option down below for you to put what your favorite telescope is. And yeah, we hope you enjoyed hearing more about telescopes, and we'll see you in the next video.